In this video, I'm going to be showing you how you can use the circular symmetry mode in AKABAK to simulate a freestanding waveguide. Similar to the 2D simulation mode, the circular symmetry mode is much more computationally efficient than a full 3D simulation. So to start with, we're actually going to go to global and BEM parameters. Now, what we're going to do is we're going to set it to 2D. The reason for this is that I prefer to check that my files look correct in the 2D mode first before opening the circular symmetry mode. This is because, as you'll see, the circular symmetry mode can be a bit harder to understand, or at the very least it's harder to see that all normals are right and that everything looks as it should. So I'm going to go to the New Components tab. I'm going to click on this, and we go to Mesh File. We're going to import a file. In this case, I have made a drawing of a waveguide, which is to be used for this simulation. So I'm going to open that one. And then we have to scale it because AKABAK believes that it is 1 meter units rather than 1 millimeter units. So set this to 1 millimeter, click apply, and here we have a drawing. However, I can see that there's some parts that are wrong here. For example, what is up with these straight lines? I don't know why these occur. It seems like AKABAK adds them of its own volition. In this case, I know beforehand that what I want to remove is everything except this component 9. So you can see this contains a lot of straight lines, basically. So I've made it with a lot of detail at the throat, where the highest detail is needed, and then it's a bit more rough through the waveguide, but it's still a ton of points, which generates a more or less smooth curve. On the back side of the waveguide, I've done a bit more rough steps, but it doesn't really matter because it affects the radiation pattern of the waveguide relatively little. Now, there's just one problem, and that is this part. Since this waveguide is going to be rotated around the x-axis, this thing will be infinitely small in practice because it's right at the x-axis. So we're going to have to remove this. And I can see here that tag, it's 9 and 377. So I scroll down until I find 377, and I can remove it. Click apply, and now everything looks good. So here we have the waveguide. This is the inner part of the waveguide. Here we have the outer part of the waveguide. And this back chamber part here is just to imitate a compression driver being mounted onto the waveguide. This line right here, 378, is the actual driver. This is just a flat disk, which is going to represent our compression driver in this case. So we click apply, and we can close this. Now that we've done this, we can go back to global and BEM parameters, and we can change to circular symmetric mode. And important, you cannot choose actual symmetry. I do not know why, but it gives you an error if you choose actual symmetry, so just say no symmetry and click OK. Now the view has changed a little bit because we cannot see the negative y-axis anymore. We only see negative, positive x, and then the y-axis. Now if we go back to the Components tab and go to the BEM tab here, we can add a subdomain. So we add a subdomain, and in this case, since we're simulating a freestanding waveguide, we are going to just choose an exterior domain. My experience is that when you're simulating waveguides, ideally you want to simulate everything as an exterior domain if you can. Now, if the model is extremely detailed, then you might have to use multiple subdomains and interfaces between them. But while interfaces are supposed to be completely acoustically transparent, my experience is that it does impact the results somewhat, even if you take great care in making the interfaces as non-intrusive as possible. So I'm just going to create a single subdomain, which is exterior, click apply, then I can close this. Now I'm going to import some elements from a mesh file, which is the drawing we have. And if I now go to drawing, we can see that it has been rotated around the axis. There's just one problem, which is that this driver, as we can see, is the wrong direction. It is, the normals are pointing inwards. And we'll fix that later. But first and foremost, we have to just remove this, because this is not part of the waveguide. This is going to be its own separate driven element. So we could see that this was element, if we click on it, you can see its element, the tag is 9376. So we just remove 376, no, excuse me. .378, very sorry about that. 376 is the back, yeah. Very sorry about that. So we just remove 378, and then we can click apply, and now we have it here. Now for some reason, in circular symmetric mode, it really likes just changing the direction of the normals. So now we can see inside the chamber. And if you can see through a structure, that means the normals, you're looking in the same direction as the normal is pointing, which means that the normals are pointing inwards here, which they're not supposed to. The boundaries is where the normal is supposed to point to. And in this case, the boundary is outwards. So we simply click on this, normal selection swap, click apply, and now it looks fine. So now we have the waveguide and the back chamber, and then it's time to add a driver. To do that, we once again go to mesh elements, and now we're going to just find 378 only, and we can see this little circle. We're going to go to boundaries, driven, and you can see here, direction normal to surface. There is a menu where you can decide how it's supposed to move, but in this case, direction normal to surface is correct. So it's just going to be moving actually in and out, basically, since it's a flat plane. But once again, we can see through the driver, and this means that the normals are pointed the wrong way. So we go back to drawing, click on this, and then we swap the normals again, apply, and now it's fine. So now we have the waveguide ready, and we're getting closer to being able to simulate. So before that, we have to go to global and frequencies, and we have to decide which frequency range we're going to simulate. Now, since the circular symmetric mode is so efficient, we can simulate from 200 Hz to 20 kHz, and let's do 256 points, for example. That's 38 points per octave. That's a very high resolution. And then we have to choose the mesh resolution. Now, for the mesh, I'm thinking we can use a mesh resolution of 0.02 or so, maybe 0.03 to make it a bit quicker. Now, this is a mesh resolution of 57 kilohertz, and this should be plenty, all the way up to 20 kilohertz. Now, you do have to keep in mind that this is with an ideal compression driver, more or less. So it's not really going to match reality above maybe 14, 15 kilohertz or so for a 1-inch compression driver. And this is just because the phase plugs of real-life compression drivers are not perfect, and they do not generate a perfect plane wave. So in reality, simulating above about 15 kilohertz is not necessarily very illuminating, but we're going to do it anyways. So I click apply. This is the mesh resolution. And now, once again, we have to go to fixed driving. And this is because, once again, we have no lumped element model coupled to this, this driven element. And so for it to radiate any sound at all, we have to choose fixed driving. In this case, I'm once again going to choose, just like in the room, the 2D room tutorial, I'm going to choose fixed driving enabled and then divide by JW. Click apply, and then we can close. Now everything is ready, more or less. We just have to decide what we're going to observe. In this case, I am interested in the contour plot, and I am also interested in seeing the frequency response of this ideal flat driver inside the waveguide. So what I'm going to do is go to the observation field, and I'm going to create a radiation polar. And now as a standard, so this one is going to be normalized radiation polar. So I go to parameters, I'm going to say this is plus minus 180 degrees in 5 degree steps. And I'm going to normalize it, and I'm going to set the normalizing angle to 10 degrees. Now the reason for this is that in general, when you have axisymmetrical devices like this, they're generally not made to be listened to directly on axis. So in this case, 10 degrees off axis is fine. For a well-designed device, you can of course listen on axis as well. There's no problem with that. So now we've chosen this, you also have to choose a position for the radiation polar. In this case, the standard position, XY, is perfectly fine. You can see here, this is the on-axis, and it starts here at the back. So it starts at minus 170 degrees, minus 175 degrees, and then goes all the way to 0 degrees, and then all the way back to 180 degrees. And then it's going to interpolate the values in between there. So now we've done that, click apply, and we're going to create one more radiation polar. But in this case, this is going to be non-normalized. So we go to range, we're going to parameters. In this case, I'm just interested in the on-axis response, so we don't really have to calculate a lot. So I'm just going to leave this as standard. And then for normalizing angle, I'm not going to do anything. This is not going to be normalized. Also, there is the option of choosing a distance. In this case, I have just hooked the far field option, which means that it's simulating very far away, something like 100 times the largest size of whatever you're simulating. But if you want to manually set it, for example, if I want to know what the frequency response at 3 meters looks like, I can do it like this. Set it to 3 meters and just remove the far field option. Now the position once again is XY, so the on-axis is in the x-axis direction, which is perfectly fine. Now I can close this, and now everything is ready. So I go to processing, I click calculate all. Now the simulation is going to take a little bit of time, but overall it's going to go fairly quickly because the circular symmetry mode is very computationally efficient. And we can see it as meshed, the parts of the waveguide here. So it's pretty high resolution. After all, this is a 1-inch throat, so it's pretty high resolution and should give reasonable results. Here we can see in purple that there is a distance problem. This one is too close to something, or it could be too close to something, which can generate issues. So I'll just let it calculate. It's going to use a little bit of time. Now, another way to check the normals, by the way, is just going to the Views tab and looking at this length of normal and direction. You can just drag this, and here we can see that the normals are pointing into the waveguide or out from the boundaries. And this is the way it should be. So you can see all of it is pointing out just as it should. And that is very good. That is how it should look. Okay, now the simulation has finished. If we go to log calc, we can see that the BEM part took 55 seconds, which is not bad at all for a simulation like this with this many frequencies and such a high resolution. But the results cannot be displayed in AKABAK, so I'm going to open VACS, and here we can see the results. So this first window, this is the non-normalized response. Here we can see the frequency response of the driver approximately at directly in front. Now, the levels are not right, so here we have to look at the relative levels. Now, as expected for this kind of waveguide, we can see that it's drooping off towards the high frequencies and also the low frequencies. I would not use this below, say, 600-700 hertz. Below that, it gives very little help to whatever driver is mounted in it. But above that, it gives a healthy bit of output boost. We can also see there's a bit of a dip right around here and a bit of a peak right around here. How real these are really depends on the compression driver you're using. It can be kind of hard to figure out just what would be real and what would not be. Now, if I go here to radiation polar, we can see this is the polar plot. It looks pretty nice. There's a nice and uniform directivity, and we have these. We have this little cursor thing which we can move around to see. If you move it in the x-axis, you see the polar plot for a given frequency. And if you move it in the y-axis, you see the frequency response for a given angle. Now, if we want to create a set of off-axis angles, we can set this to 0, and then we can double-click on this curve, and we can set it to 10, double-click on this curve, set it to 20, double-click on this curve, 30, double-click on this curve, 40, double-click on this curve, 50, double-click on this curve, and so on until you have gone all the way from 0 to 90 or 180 degrees, or whichever frequency you want, in whatever increments you want, really. In addition, this is a pretty rough contour plot, so let's just change it up a little bit. We're going to shift a range, we're going to turn off shift range, and then we're going to set this to 0, so we only see half of it because it's symmetrical. And we're going to set this to 200, so it fits the part we've actually simulated. And then we can set this to 3 dB steps instead of 5 dB steps, so we can see more clearly what is going on. If you want, you can even set it to 2 or 1 dB. This is really up to you. I prefer to look at it in either 2 or 3 decibel steps, but it's entirely up to you. If I set the max to 0, then we get this convenient little graph. And here we can see that -3 is the black outline here, -6 is the black outline here, -9 is the black outline here, and so on. You can also click here and just drag this up to have the outline at a given level. So here we can see level marker is -11 decibels. So this is the angle at which it reaches -11 decibels. Now, if we want the beam width, we can pull this to -6 decibels, and then we can look at the beam width graph. And the beam width graph is down here, and we can set this to, say, 0 to 180 if we want, and we can see this only gives half the beam width though. So for actual beam width, you have to multiply the number you see here by 2. In this case, it's quite smoothly going towards about a 45 degree, which is 90 degrees beam width at the top end, and it slowly expands towards the lower frequencies. At 1 kilohertz, it's about, I would say, 105 to 110 maybe degrees beam width, and then it widens as you go lower. Sometimes this visual bugs out a little bit. You can see it here as well. The red line, the upper contour is kind of strange. But for the most part, it's nice enough to work with. Now, another thing that may be of interest to people designing waveguides or horns is the radiation impedance. So if we want to see the radiation impedance, we can go back to AKABAK again. And here we have our driver, which we simulated. And we go to the observation tabs. And then we can just choose radiation impedance. Click on this, and then we choose the elements. Now, in this case, there's only one element that is driven. So it's only one thing it can observe the radiation impedance of, the normalized radiation impedance, and that is this driver right here. So we just click apply, and we close, And then we can go to processing, and then instead of calculate all, we can go to calculate individually, and we can choose spectrum radiation impedance. You can also do spectrum all if you want. That would recalculate the polar plots and such, or the contour plots. In this case, we don't need that, so we just click spectrum radiation impedance, and then we open VACS, and now we can see that we have the radiation impedance, the normalized radiation impedance. And it looks about as what you'd expect. It has a slightly higher radiation impedance than 1 at the upper end, but then it smoothly falls off towards the lower end, which is what you'd expect from most constant directivity waveguides or horns. I hope you find this useful. If you have any questions, do not be afraid to ask. Thank you very much.